Welcome back to Chem 4300. In this video, we're going to continue the topic of chemical kinetics. And now we're going to focus on how the reaction rate constant depends on temperature. And this is a story that begins with the Swedish physical chemist Svante Arrhenius, who in 1889 proposed this relationship from his empirical experimental measurements in the lab. And what he found was that if he plotted the log of the rate constant measured at different temperatures, if he plotted that rate constant times versus 1 over the temperature, then that the rate constants, and so here for this example, it's NO2 going to NO and O2, the rate constants given by these black dots follow fairly linear relationship in this curve. So in this plot, we see that the log of K versus 1 over T is fairly linear as you vary the temperature and measure the rate constant. And that he expressed with this equation here. Now don't forget that this is a 1 over temperature plot. So this is the high temperatures over here. These are the low temperatures. And so rate constant is increasing as we increase the temperature. So this activation energy is what he assigned to the energy that's needed for the reaction to occur. It's a barrier that prevents the reactants from getting over to the products. And one way of sort of imagining that is a sort of picture where the reactants have one particular energy, the products have a lower energy, but they're kept from being transformed from reactants to products by a barrier which has an energy associated with it, which is called the activation energy. And it's only by increasing the temperature that the molecules get enough energy to overcome this barrier to go from reactants into products. And if you remember from the chapter on the kinetic theory of gases, we plotted the probability of energy or kinetic energy as a function of energy. And we had these plots, and I've taken that plot from that chapter and turned it 90 degrees so that energy is up and energy is up here. And you can see that as you might imagine, that as you increase the temperature, the fraction of molecules with that energy and higher to get over that activation energy increases as you increase the temperature. And that's sort of the reasoning behind the Arrhenius equation, that the energy is going to have this exponential form. Now, it generally works for most cases, but there will be cases where you'll see that the activation energy actually is not independent of temperature. It varies a bit as you change the temperature. So you'll see then in the plot of the log of K versus 1 over T that it's not linear. There'll be some curvature to it. And so in that case, we can still use Arrhenius's idea. We'll just take the activation energy as the slope of the log of K versus 1 over T at any point along the 1 over T curve. So we'll define the activation energy in this more general form as RT squared of the derivative, the slope of dln K dt here. Now, another way that we can sort of approach this, it's a little bit more mechanistic, is to use something called transition state theory, from which we're going to get this expression is called the Eyring equation. And this is going to involve the temperature, as we expect here, but it's also going to involve the equilibrium thermodynamic properties of something called the transition state. And we're going to come to that here in a bit. So this expression here will allow us to sort of think a little bit more about the mechanism of how that reaction occurs and why it has that dependence on temperature for its rate constant. So imagine a reaction, let's say, I'll write it down here, like this one here, where I have a diatomic molecule, AB, reacting with an atom, C, going to an atom and another diatomic molecule, BC. So in other words, C is going to collide with this molecule, knock the A off, and form a BC molecule, and the A is going to go flying off. Now, how do we describe that reaction in terms of some kind of potential energy surface? Well, let's first start with looking at the potential energy surface for just one of those diatomic molecules, say the AB molecule, and we know that as the distance between A and B changes, the potential energy between those atoms has this form here. We've seen this throughout the course of the semester here. So there's a minimum potential energy where the force acting on the atoms is 0, and this is where the equilibrium bond length is. Similarly, for the BC molecule, we'll have a similar curve for this molecule, and it will have its own equilibrium bond length where the potential energy goes to a minimum. And these two molecules may have different absolute energies differences, right? So in other words, this one down here has an energy that's lower at the minimum than the AB molecule. So there's differences, I should say relative differences in these energies here. So what we want to try to do is imagine how we're going to describe this reaction on some kind of potential energy surface. Well, obviously these 1D plots are not going to cut it, so we need to come up with some kind of multi-dimensional plot. And the way we're going to do it is we're going to pretend that the AB diatomic molecule is going to collide with C, and all of it is going to occur on a line, so that it's all there's no angle dependence here. It's just a head-on collision of C directly onto B, attaching and knocking A out. Okay, so this is the picture that we have. So imagine our AB molecule, C is coming in a collision course. It's going to hit B, form a bond, and A is going to go off in the other direction. It's a limited possibility of all the possibilities, but it's enough for us to understand the concepts that we need here. And so the way I'm going to draw the potential energy diagram is I'm going to look at it from the point of view is that when C is far away, then this is what the potential energy diagram looks like. And when A is far away, this is what it looks like. So this is the diagram I have. If you just take a cross section here, here's that curve for the BC molecule with the equilibrium distance here. And then if you look a cross section this way, this is the curve for the AB molecule with the equilibrium distance here and the C molecule far away. So this is the BC distance being really large. So you have to stare at that and think about it for a while, but that's a two-dimensional potential energy surface for this head-on collision here that we're talking about. So there'll be, as these C atom approaches, as I bring the BC distance down, then you can see that the potential energy will go up, and we will reach this saddle point right here where we have A, B, and C very close to each other, and then we will find that the A atom will then detach, and we will fall into this new minimum here where now we have B and C at its equilibrium length and A will be further away. So this 2D potential energy surface, if I sort of took a line and drew it here along there through that saddle point this way, would give me this curve right here. And here I have on this side the AB with C coming at it, and now I have BC with A leaving. And at this point right here, corresponding to this black dot, I have what's called the transition state, the state where A, B, and C are the closest, and that's at the saddle point of the contour plot. And what we're going to do with transition state theory is we're going to describe the kinetics, the rate constant for this reaction in terms of the thermodynamic properties of this transition state. So I'm going to write now that the transition state is formed by a reaction of two species, A and B, to form the transition state to go to a product. Now, there's an unfortunate use of symbols here. I should have changed this, but A and B just represent two molecules that are colliding to form a transition state, and then P forms the product. A and B have nothing to do with the atoms that I drew here on this previous slide. I probably should have called them, I don't know, E and F would have been better. So anyway, A and B in this case represent two different molecules coming together to react. They form this transition state, and then that transition state can either go back to A and B, or it can turn into a product P. And we're going to write the mechanism down like this here. and the A and B and this transition state are in equilibrium with each other. So they'll form the transition state, and then it will break apart and go back, or it will form the transition state, and sometimes it will go to the product, and then the reaction is complete. So we're going to describe this part as an equilibrium. Again, this is very similar to what we saw in the previous videos. And we're going to write that equilibrium constant this way. And I'm going to scale these guys by 1 molar, because these are going to be in terms of concentration, an equilibrium constant written in terms of concentrations here. And the rate constant for the transition state to go to the product will be something that will come from statistical mechanics, and it's related to the vibrational motion of the transition state. And I can't really get into it in this semester on how that works, since we don't really cover stat mech, but we'll just leave it at that to say that this is a vibrational frequencies that are associated with the transition state that is related to that gives us the rate constant for X decomposing into the product. So taking all that together, the rate of formation of the product is this nu times the concentration of the transition state. The concentration of the transition state we can get by rearranging this expression here to write it in terms of the concentration of A and B and this equilibrium constant. Okay, and now we can take the expression here that we get from stat mech for nu, replace that, and now we have it, all these terms grouped together. We'll call this the rate constant K. So for this reaction, the rate of the reaction is K times A times B, and we have an expression for K which depends upon temperature and this equilibrium constant. So let's keep going with this. But before I go, one thing I want to say is that, we can't measure this directly, but we're going to infer information about that from the actual rate constant. So let's keep going then and take that reaction, which we've written this way with this new definition for our rate constant, and let's use some thermodynamics that we can apply to this transition state. And we know for an equilibrium constant that the delta G is related to the equilibrium constant through this simple relationship here. So minus RT log of the equilibrium constant. This is something you might remember from freshman chemistry when you start learning about thermodynamics for the first time. Here we see that rearranged so that it's written as e to the minus delta G over RT. And we also know that the Gibbs free energy is related to the enthalpy and the entropy change for that reaction here with this expression. So I can take this further and divide it up into 2 terms for the enthalpy and the entropy. And these are, again, the thermodynamic quantities associated with this reaction here in there. And so taking that expression and plugging it into this expression up here, I now have my expression for the rate constant, which is the Eyring equation, which I showed at the beginning of this video. And this expresses then the rate constant, which has a temperature dependence, both here and over here, but also in terms of the entropy and enthalpy change associated with the formation of this transition state. So it's a little weird because we're talking about kinetics, which is non-equilibrium situation, but we're using equilibrium thermodynamics to describe this reaction that's part of this mechanism here. So let's see if we can work out then how to relate this expression that we just derived, Eyring's equation, to the parameters that's in the Arrhenius equation, which Arrhenius had worked out empirically. So we had this very general expression from the Arrhenius equation, which is the activation energy at any given temperature. So let's use this and this expression and see what we can learn. So first we want to calculate dln of k dt. So let's take ln of k, is just that guy, taking the log, expanding it out, gives us this term. then taking the derivative of this with respect to temperature. So that's going to be this and this, which then evaluate out to this term here. And then finally, plugging the rest of that into the Arrhenius expression, we'll have that expression. We plug these in, and we get this expression, which then simplify to this expression here. So now we see that the Arrhenius activation energy is related through these expression here to the equilibrium constant and the temperature. So before I go any further with this, I have a little assignment for you to do to prove. I don't want to get into the details of all of this, but for a gas phase reaction that's given here, which has this equilibrium constant that's based on pressure and this equilibrium constant based on concentration, there's a relationship between these equilibrium constants that you can show that the concentration-based equilibrium constant is equal to the pressure-based equilibrium constant with this conversion factor here, where delta N comes from these stoichiometric coefficients up here. So prove that, to verify that this relationship is true. And then additionally, there's something called the Van Hoff equation. And from the Van Hoff equation, which involves this pressure-based equilibrium constant, you can prove that the concentration-based equilibrium constant will obey this relationship here, where we're using delta U instead of delta H. So I'll leave this for you to prove, but now I'm going to go back to this expression where we have, I'll go back here real quick, this is in terms of the concentration-based equilibrium constant, which is written right here. And so for what I just proved, well, I asked you to prove, which was this equation here, that from that equation we can rearrange it to give us this form, and we recognize that is that there, so that means we can make a substitution here, and we can write that the Arrhenius activation energy is RT plus delta U for the reaction that is the formation of the transition state. So let's take it one step further, and let's say we're going to use an ideal gas for our reactants and products. So then in that case, we know that the delta H is equal to delta U plus P delta V. And for an ideal gas, P delta V is just delta N RT. So making that substitution allows us to rearrange this expression into this form right here, and then rearranging it, we finally get it into this form where we have a relationship between Arrhenius's activation energy and the delta H and delta N for the formation of this transition state. Okay, and now we have what we need to relate our rate constants back to the thermodynamic properties of this transition state. So here's our activation energy expression. Let's take something like a unimolecular reaction where A is going to this transition state. So the N final for the reaction is 1. The N initial for the reaction is 1. So delta N for the reaction for the formation of the transition state is 0. Put a 0 in up there, and you get a delta H, which is just activation energy minus RT, right? That means that the K expression becomes this here, and we can then simplify this a little bit more, and we finally end up with this expression where K is equal to a pre-exponential term times e to the minus EA over RT. This is what we predict for the Arrhenius-like behavior, but now our pre-exponential term depends on temperature and the entropy change for the formation of the transition state. So let's take a look at that here in a little bit, and actually we're going to look at this example in a little bit. And we'll look at the bimolecular reaction. So this was unimolecular. If we do bimolecular, A and B come together to form a transition state, then you see that an N final is 1, N initial is 1, 2. So delta N is minus 1. Put that minus 1 in up there, and you'll have an expression for delta H. Work through these same steps, and you'll get this expression for the rate constant. And you can see it looks very similar. The main difference here is that this is Euler's number, and this is Euler's number squared. It's actually a little unusual sometimes. I think you're not used to seeing Euler's number all by itself there, all by, without anything raised to it being raised to any power. But that's just Euler's number there, and here it is squared in this expression. here. So that's unimolecular and that's bimolecular. So let's take a look at an application where we have, for this reaction, we know the Arrhenius activation energy and the prefactor, exponential prefactor. The activation energy is 15.5 kilojoules per mole, and the prefactor is 1.09 times 10 to the 11th liters per mole second. And we want to get the delta H and the delta S for the formation of that activation, the transition state. So we're going to assume ideal gas behavior. So using the equations that we just worked out, so let's go back here real quick here. So for delta H, when you put in a -1 here, you got 1 minus -1. So the delta H for bimolecular, which I didn't write down, is delta H. Sorry, I made a mistake there. That's supposed to be a minus sign there. It's supposed to be activation energy minus 2RT, which you would get by just putting in a delta N of -1 there. So I'll correct that. And when you take activation energy minus 2RT, and here it is, you get this value for the delta H of minus 1.13 kilojoules per mole. And then for the entropy, you can take this expression, which is equal to the pre-exponential factor, and rearrange it into this form, where here's that A, the pre-exponential factor, and when we set that up with the numbers for the pre-exponential factor A, we have the temperature here, Boltzmann constant, Planck's constant, and Euler constant. All of those together will give you a value of minus 60.3 joules per mole Kelvin. So now we've calculated the delta H and the delta S associated with the formation of this transition state from the Arrhenius activation energy and pre-exponential constant. Okay, so that's it for this video. In the next video, we're going to be looking at kinetics of reactions and solutions.